Good day and welcome to today's class. In today's class, we are going to state the necessary and sufficient condition for Riemann integrability, and we will try to prove it. Necessary and sufficient condition for Riemann integrability. A bounded function f of x on the interval AB is Riemann integrable if and only if for each epsilon greater than 0 there exists a partition P of AB such that the upper Riemann sum minus the lower Riemann sum is less than epsilon. This is a two-way proof, and so we'll prove the first side and then prove the converse side. What does the first side says? It says that let f bounded on AB be Riemann integrable if f is Riemann integrable, then for epsilon greater than 0 there exists a partition P of the interval AB such that 0 is less than or equal to the upper Riemann sum minus the lower Riemann sum, and this is less than epsilon, and this is less than epsilon. That's what we want to prove. But recall from our definition of Riemann integrability, we said f of x is Riemann integrable if the lower integral equals the upper integral. That is, the integral from a to b of f of x, a function, is Riemann integrable if what? The lower integral equals what? The upper integral. The lower integral equals the upper integral. Let's call this our equation 1. Let's call that equation 1. Then, by Darboux theorem, for each epsilon greater than 0, there exists a delta greater than 0 such that what? The upper Riemann sum is less than the upper integral of f of x dx plus epsilon over 2. Call that equation 2. And then the lower Riemann sum is greater than what? the lower integral minus epsilon over 2. Call this equation 3. But recall that from equation 1, that what? The integral from a to b of f of x dx is equal to the lower integral, and it's also the same thing as the upper integral. If that is the case, what happens next? It means that I'm going to replace this with this one. That tells me that my upper Riemann sum is less than the integral of f of x over the interval a to b plus epsilon over 2. I call this equation 4. And my lower Riemann sum is greater. I also replace this by the integral a to b of f of x dx minus epsilon over 2. I call this what? Equation 5. By the time I bring epsilon over 2 here, I have the lower Riemann sum plus epsilon over 2 to be greater than the integral of f of x dx. And if that is so, that tells us that the integral of a to b of f of x over the interval a to b will be less than, if this is greater than this, then this is less than this. The lower Riemann sum plus epsilon over 2. This is less than that. By the time we add epsilon over 2 to both sides, we have the integral of f of x dx plus f of x dx plus epsilon over 2 to be less than the lower Riemann sum plus epsilon over 2 plus epsilon over 2. For this expression, the upper Riemann sum is less than this, the integral of f of x over the plus epsilon over 2, and this is less than what? The lower Riemann sum plus epsilon. That is less than the lower Riemann sum from epsilon. I can do away with this one, and so I have the lower Riemann sum to be less than the upper Riemann sum rather, to be less than the lower Riemann sum plus epsilon. And by the time this comes here, the upper Riemann sum minus the lower Riemann sum will be less than epsilon. But the upper Riemann sum minus the lower Riemann sum will always be greater than or equals to 0. The upper Riemann sum minus the lower Riemann sum will always be greater than or equal to 0. What do I mean by that? U of f with respect to p minus L of f with respect to p will always be greater than 0. Therefore, 0 is less than or equal to u of f with respect to p minus L of f with respect to p, and that is less than epsilon. That proves the first sides of the necessary and sufficient condition for Riemann integrability, where P is a partition of the interval AB. That is, P is element of that. Now we'll try to prove the converse side. Try to move back in the reverse form. We'll try to prove the reverse of it. Remember we said that it is a two-way proof because of the if and only if. If it is Riemann integrable, then this. And that's what we have been able to show there. However, if this occurs, can we be able to show that it is Riemann integrable? That's the converse which we want to prove now. Conversely, if 0 less than or equal to this, the upper Riemann sum of f with respect to p minus the lower Riemann sum of f with respect to p, if that is less than epsilon, for each epsilon greater than 0 and a partition p of the interval AB, we want to show that that implies that our f or f of x is Riemann integrable. Recall again that f of x is Riemann integrable if the lower integral equals the upper integral. F of x, by definition of upper Riemann integral, our u of f, which is the same thing as this, is equal to the infimum of the upper Riemann sum of f with respect to p, where p is a partition of AB, of the interval AB, where p is a partition of the interval AB, and then also our lower Riemann integral L of f, which is also this by definition, is the supremum of the lower Riemann sum, the lower Riemann integral L of f is the supremum of the lower Riemann sum of f with respect to p, where p is a partition of AB. If that is the case, then this will be greater than the lower Riemann sum. is greater than or equal to the lower Riemann sum of P with respect to, we call this equation 6. Multiply both sides by -1. This gives me minus the lower integral will now be less than or equal to minus the lower Riemann sum. I call this equation 7. Equation 7. Also, we do the same thing for our upper Riemann sum. Our upper Riemann sum from here, the upper Riemann sum, which is this, of f of x dx, and we said it is equal to what? The infimum of the upper Riemann integral, where P is a partition on interval AB, and if that is so, that tells us that this, the upper integral of f of x dx, will be less than the upper Riemann sum. I call this equation 8. Equation 8. And so I will add equation 6 and equation 7 and equation 8 together. Adding equation 7 and equation 8 together. What do we have when we add equation 7 and 8 together? We have the upper integral minus the lower integral to be less than or equal to the upper Riemann sum minus the lower Riemann sum. But these two, they are less than epsilon. That is the integral, upper integral minus the lower integral is less than or equal to this, and this is less than epsilon. This implies that our upper integral minus the lower integral is also less than epsilon. But the upper Riemann sum minus the lower Riemann sum will also be greater than 0 always. U of f with respect to P minus L of f with respect to P will always be greater than 0 always. If that is the case, then the upper Riemann integral minus the lower Riemann integral will also be greater than 0. That is, the upper integral minus the lower integral will be greater than or equals to 0. That tells us that 0 is less than or equal to the upper integral minus the lower integral, and it is less than epsilon. If that is so, from there, if that is so, it means the upper integral minus the lower integral is equal to 0. That means this equals to that, upper integral is equal to lower integral. And remember, we have said by definition of Riemann integral that if this is true, then our function f is Riemann integrable. Our function f is Riemann integrable. Therefore, we have been able to prove the necessary and sufficient condition for Riemann integrability, which says that if f is Riemann integrable on the interval AB, that f is Riemann integrable on the interval AB if and only if for epsilon greater than 0 there exists a partition P on that interval such that 0 is less than or equal to the upper Riemann sum minus the lower Riemann sum, and that is less than epsilon. That is the proof for the necessary and sufficient condition for Riemann integrability. Thank you. God bless you. You can attempt this proof also and see if you can be able to prove the necessary and sufficient condition for Riemann integrability. Thank you. I see you in the next video.